Yeah, so recording is on. Thank you everyone for being here. I can see a lot of new participants and a lot of very, very welcomed and old ones, together with contributors. Thank you very much for being here. And as you could see from the tweet and as you could see from the announcement in the Telegram chat, today our call will be mostly devoted to presentation. Maxim will do the slides, and I will do the video recording of the slides. So just giving you a heads up in order to preserve your privacy. Do not do that, please. Yeah, so I think we can start. Maxim, the stage is yours. I think you can start sharing the screen or start describing the narrative of today.
Yeah, I will do the brief introduction and then we'll proceed to the slides.
Yes, perfect.
So the idea behind today's call was that, in fact, over the last week and before that, but also during the past week, we have a number of people joining the project, starting contributing and participating. We have very good pull requests. We have a new issues opened, and we've got a lot of questions, both me and Olga, about RGB. And all those people, they are developers, and they need to understand the internals of RGB protocol. And the questions are nearly almost the same. So the idea was to have a discussion and presentation that will explain, actually it will be a set of presentations over this week and the next weeks. If we will require more time, we will probably dedicate a separate call, technological call for that. But we decided to start with a general call and giving this presentation on the first initial presentation on the overall call that we have on Wednesdays, to give an introduction into the technical internals of RGB protocols for all those new developers who are joining in, and to address most common questions. We already had a few discussions, deep technological discussions regarding RGB before that. The first one, the first one which was publicly recorded, had taken place in Milano in December last year. There was a 3 days non-conference where I was giving a lot of insight onto the current state of those days of RGB protocol and all related technologies. And we invited many existing contributors to RGB and people from the community who had contributed during the conference a lot into further RGB development. We have a video recordings and presentation of all those 3 days. There is more than 300 slides and more than probably 20 hours of video recording. However, first of all, a number of same things had changed since that time. And during the Milano conference, RGB wasn't finalized in many aspects, and many things had changed. And also, there were a lot of details which were not related directly to RGB, but more like introduction into cryptography and other related concepts. So I wouldn't advise you to spend like more than 20 hours of listening to that. And the idea was to give an update on the state of RGB as of today. We already had tried, the second attempt was during the spring this year. It was like 2 or 3 months ago. I gave a single presentation, which was quite a long presentation on RGB technology, very deep internals of the code and modular system of the library, and deep coverage of the deterministic Bitcoin commitments part. But first of all, it was very specific and narrow. And unfortunately, we had to move to other questions, so we hadn't time to give this further technological deep insights because I briefly described nearly a quarter of RGB system only. And it was quite complicated. So throughout the time that passed since that presentation, the RGB have moved forward. I wouldn't say that something changed at noticeable scale. No, there was a lot of changes like bug fixing and small internals and improvements, but the overall design of the technology hadn't changed. However, you know that with the time, explaining over and over the technology again and improving it, you understand how to explain it in simpler words and better. And actually, I would say that with the last presentation this spring, I will starting from very deep internals, not directly related to RGB, and it's really hard to grasp the overall concept. So what we are trying to do right now is we're trying to do a complete coverage of RGB technological internals, starting from upper layer, going inside, and explaining that in technically simple words, meaning that this presentation will be intended for developers. And for non-developers, it probably will be hard to understand it. However, for everybody who is quite familiar with Bitcoin or Lightning Network, it would be not that hard to understand, and it will represent the coverage of RGB, starting from the overall overview of the RGB, moving into probably we will have 3 or 4 more presentations, moving into specific aspects. The aims that we have is, first of all, give the overall understanding how RGB is composed and what part it is consists of, what are the modules, point out to specific repositories and specific code locations inside the project, because we do really have new contributors today, and we need to make them understand where to look to some specific functionality. And after the presentations, starting from the next one, when we will go to the code directly, we will be announcing a public program. I would say, well, first of all, it would be a bounty program for finding bugs, and the second, it would be a program for paying for writing test coverage for the RGB library. So I will be explaining module by module, and it will help the community to develop more tests for different parts of RGB library. So we will be gradually making sure that RGB technology is community reviewed and covered in different aspects by the tests. So this is the overall background why we are doing these sessions. Again, as I said, because the Wednesday's calls, they are more generic. It might be that we will move this deep technological overviews into the other part or other day, just to keep the Wednesdays for more generic questions. But we decided to start for now with the pre-existing date of the calls. So I will start in a moment. If anybody have any questions regarding this introduction or something to add, you're welcome to say something. Okay, I assume that we are all fine to start the presentation. So I will start with the slides. Do you see the slides?
Yes, we can see the slides.
So you see the slide full screen, correct?
Yes.
Not the application. Okay. So I will proceed now. What I would like to start, again, as I said, the last time I tried to go from the very deep internals like deterministic Bitcoin commitment, single-use seals, up to the RGB. And it was really hard to grasp, because without seeing how RGB is working and performing overall, it is really hard to understand why we need these specific commitments, very complicated stuff. So this time I decided to move from the top to the bottom. So today I will give an overview of how the RGB is structured And with the next presentations, we will go into each particular detail of the technology. I will start with a generic definition of RGB. And namely, today, I would try to put the definition of RGB in 3 different forms. The first one is like public market definition for those who are not very deep into the technology. The legal definition, the final one will be a computer science definition. So I will go deeply through these definitions to unveil the essence of RGB. So what is RGB? It is, at the very simple way of explaining, it is smart contract layer on top of Bitcoin and Lightning Network, which with a strong emphasis on privacy and scalability. And while it's being mass market definition, I may say that if you being technically skilled, you will eventually find that nearly each word of this definition is wrong. So it allows you to explain to journalists and other public community what it is about. But the fact is that when we say that RGB is a smart contract system, we need to explain that it's completely different smart contract system to what usually is understood as a smart contract systems. And today I will pay a very brief attention explaining why it is very different from Ethereum type of contracts or other types of smart contracts. And again, the smart contracts is a very vague term that is being widely used for different purposes. So we need to quite strictly define what RGB allows and what not, and it will be shown on the next slides. The second part is that it is basically a layer on top of Bitcoin and Lightning Network. Again, we need to define what layer is, but basically it operates on top of Bitcoin and or Lightning Network, but it's quite different in its nature to these networks because Bitcoin, for instance, has a global consensus. RGB doesn't have a global consensus. And the direct implication of that is that with Bitcoin, you have a network of nodes being online and agreeing with each other on the state of the system. With RGB, you still have nodes, but they are very much unlikely to Bitcoin nodes. It's nothing that is commonly understood as a blockchain system. RGB is not a blockchain at all. It is based on Bitcoin blockchain, but it performs and operates quite in a different way. And yes, it's true that it has a strong privacy and scalability emphasizes, but again, many parties understand privacy and scalability in a very different way. The way we understand it with RGB is that privacy should be a cypherpunk for the determined privacy, meaning that it's not like it should be private from the world, but regulators can explore, or there might be chain analysis on other tools that can unveil the actual transactions. No, with RGB, we are aiming for as much privacy as we only can, and the only party that should know the whole history and all the data should be the owner and nobody else. Well, it's a goal. It's not easy to achieve in many cases, but that's the design value that we put into the system. And with the scalability, RGB, it's not scalable by itself. It utilizes the fact that it operates on top of Lightning Network, which is scalable, and it utilizes the fact that it doesn't put any additional data to Bitcoin network, not to Bitcoin transactions, and it does not reduce the scalability because of that. So that's a mass market definition. If we will go one layer deeply, I would say that, in fact, RGB is a digital right ownership management system. So it manages ownership of digital rights. Why digital? Because with the digital world, we can't define anything that is not digital. So basically, it's right ownership. It's ownership. So who is the owner of the rights? That's the main aim that RGB should be answering for. So if you even think about such things as assets, tokenization, there is always an owner of these assets. And RGB basically, instead of managing tokens or assets, it manages the ownership of these assets and tokens, first of all. And as I said, it is confidential and censorship resistant, and it is built on top of Bitcoin and Lightning Network. So RGB, in a more strict sense, is a rights, the management system for rights ownership. How it works? The rights are assigned to Bitcoin transaction outputs, meaning that the owner of this particular right is a well-defined the owner of Bitcoin transaction output. So if it narrows down the whole right management to the Bitcoin ownership management. And basically, with RGB, we are not inventing the wheel. We are not trying to create something better than Bitcoin in terms of security, in terms of the rights management. If you can spend some specific Bitcoins on a transaction output, you are the owner of the right assigned by RGB to the same output, if there is any right assigned to this output. So, and in this way, coming back to the question that we had about the taproot, you can utilize arbitrary complex rights systems until they are supported by Bitcoin transaction itself. So today you can have multi-sigs or Lightning Network specific HTLCs, or tomorrow you will be able to do a taproot scripts. The rights are managed by Bitcoin layer, not by RGB. We are just using Bitcoin transaction outputs, not adding any data to those outputs at all. We just agreeing between us that we assign some ownership of some rights to this specific transaction output, and the rest is done by Bitcoin itself. This is quite important because basically it reduced a huge load about the audit and validation that RGB doesn't have security leaks, so you can't stall the funds. It's quite clear. If you can't stall Bitcoins, you wouldn't be able to stall RGB rights. If you will be able to stall Bitcoin, you will be able to store RGB rights. So basically, we delegate this question to Bitcoin layer itself. And of course, not only just Bitcoin, but Lightning Network, again, the Lightning Network itself. So if anybody has the question, is something is possible with RGB, or would my coins be lost if RGB channel, if Lightning channel is closed in a non-cooperative way? Again, this with your rights, it will the situation with your rights will be exactly the same like situation with your Bitcoins in that channel or on that transaction output. Whatever will happen or will not happen to Bitcoins will happen or will not happen to RGB. There is no right management in RGB other than the management of Bitcoin transaction outputs. And what RGB then adds to the Bitcoin, because it's basically only comes down to the Bitcoin transaction output management, what RGB is about? Well, RGB adds the rules for and formats for the state. So the rights can be very different. It might be a coins, it might be identity, it might be something else, and these rights are connected with some state. And when you assign the rights, you also frequently attach the state. And you also define additional rules that are applied on top of Bitcoin script rules to the rights management. So, meaning that while you wouldn't be able to lose your rights until the Bitcoin transaction output is spent, there might be an improper way of spending Bitcoin transaction output. So if you will spend the Bitcoin transaction output in a wrong way, not compatible with RGB rules, you will probably also lose your rights. Not to some other party, but just lose them forever. Meaning that it requires some specific Bitcoin wallet support and so on and so forth. So while RGB relies on Bitcoin for managing rights, it imposes additional rules on top of Bitcoin rules, which are not related to the rights management, but which are related to the evolution rules of these rights. And let me explain that in more detail. So with RGB, there always must be an owner. The smart contract state, unlike in case of DAOs and Ethereum and so on and so forth, is not a public good. It must always have a well-defined ownership. And this ownership is defined by transaction output, as I already said. So whoever, a corporation or party, multi-sig, taproot-based, owns Bitcoin transaction outputs, this party owns the rights related to RGB state. RGB defines ownership by binding, assigning state to Bitcoin transaction outputs, as we already discussed a lot of times, using single-use seals. And I will spend much more time covering and explaining that part a bit later. And state ownership is not equal to the state validation. So ownership defines who can change the state. So the Bitcoin script in the Bitcoin transaction output defines who has the right to change the ownership. So who is the current owner and who can pass this right to some other party. While RGB implies additional validation rules related to client-side validation, which define how the right may change. For instance, while you can spend your Bitcoin transaction output and pass your rights to another party, you can't create additional coins when you do that transfer. And this part is not defined by Bitcoin script. It is defined by RGB specific functionality. And this separation of two layers of state ownership and state validation is very important. And it puts RGB very much aside from existing smart contracting system. Also, it makes possible for RGB to operate on top of Lightning Network and other potential future layer 2 solutions like multi-party Lightning channels. And basically, you can have atomic swaps or any kind of advanced Bitcoin technologies, DLCs with RGB, whatever you are requiring, without any changes to RGB itself, because of this separation, which is absent in any other smart contracting system. So, finalizing this part, I would like to give the most deepest RGB definition in terms of computer science. Me and Christian Decker, we are trying to prepare the scientific article, which will be explaining RGB in these terms. It's still work in the progress. I think it will take like 5-6 more months to prepare. But anyway, I would like to give a brief preview of that RGB is in fact a distributed system of partially replicated state machines, meaning that like with a Bitcoin, you have a replicated state machines. They replicate the same state or blockchain over all the nodes in the Bitcoin network. With RGB, you have a partially replicated state machines, meaning that only owners of some specific information and rights will have the data about those rights, and they do not replicate it to the rest of network, which guarantees quite prominent confidentiality and privacy properties. And there is no globally known state. So the RGB is distributed system of partially replicated state machines without globally known state, having nearly synchronous state consistency enforced by a consensus protocol of the underlying layer, meaning that it's very interesting that by combination of Bitcoin, which is a globally replicated state machine, and having its own global consistency because of consensus protocol, proof of work consensus protocol, and having RGB on top of it, which is partially replicated with a strong confidentiality properties, we are able to achieve the situation where we rely on the consensus of Bitcoin network, but itself RGB doesn't have a global consensus, ensuring this confidentiality that we are seeking for. So, and again, I forgot to tell at the very beginning, please interrupt me if you have any questions or comments, because the topic is still quite hard. I spent a lot of time trying to make it simpler, but I don't think that I was very successful in that. And just interrupt me and ask you a question. So I will take a breath, and you have time to give the questions.
Yes. So awesome that you took pause. There is a question. Well, not a question, but a comment in the chat of this call made by Bob. I think, Bob, if taking into account that we're having a break, you can just speak up and make your comment out loud. Or not. Okay.
Can you read it, please? Yeah.
Sure. So Bob wrote that my understanding is that simplicity is not Turing complete, and this isn't needed. It doesn't have unbounded loops. I have no idea what exactly this comment means and how it can be introduced into the
Can you guys hear me?
current topic. Yeah.
Oh, sorry, I was muted. Yeah. So my understanding is that through Post's theorem, simplicity is not Turing complete. It doesn't have unbounded loops. It unrolls all loops essentially, and that Turing completeness is not necessary. I think this is a red herring the Ethereum community throws around. Anyway, just if I'm incorrect, correct me there.
Well, both of these things are mostly true, meaning that simplicity is not Turing complete, but there are very different levels of non-Turing completeness. And
yes.
Comparing to Bitcoin script, it's much closer to the Turing completeness. And frankly speaking, I once had a very interesting chat with a cryptographer who explained me that there is no Turing complete language in the world if we will take it really seriously to examine all of them. But again, on the practical level, so there is a difference between scientific definition and technological application, because for technological and engineering purposes, it's frequently you don't need a scientific purity. You need something that works in the 99.9%, and that's all. And in these terms, the simplicity, I think, is a very good trade-off, have a very good trade-off set between the Turing completeness and safety properties and formal possibilities for formal analysis. So I doubt that you will need a Turing completeness for the tasks that are related to RGB, meaning rights management. And I still think that it's much better to have simplicity than something that is so-called Turing complete in the normal blockchain world. But again, you see, the Turing completeness, it's very funny, because the Turing completeness is defined as ability to write a compiler. Well, one of the definitions. You can write a compiler to this language using the language itself. But it's not, but if you will examine, for instance, Ethereum and EVM, you will find out that such concepts as a time or randomness, they are absent in Ethereum virtual machine, because they're impossible to have in decentralized environment. And while the EVM is nearly Turing complete, it still doesn't mean that this language is sufficiently expressive to express all the situations that you require in smart contracts. So my conclusion is that Turing completeness is not the end goal, and is not very good and performant criteria. It's more like mass market term that everybody applies. So this is Turing complete and this is non-Turing complete. And simplicity is very near in terms of Turing completeness to EVM and WASM, but it's much safer than AVM and WASM. And for sure, it's much more functional than Bitcoin script. So that's probably the bottom line that is really important.
However, it's interesting and important distinction between what does and Turing completeness, and by simplicity that is valuable is the ability to do formal analysis and prove the contract does what you think it does. That is not on Ethereum. That's why they have gas, things like that. And I think that is a feature, not a bug, that should be, I don't know, advertised, rather than trying to phrase things in Ethereum's terms and say it's Turing complete. That's all.
Yeah, no, that's a good point, and I will agree with that. Do we have any other questions? Okay, I will continue. So, giving the definition of RGB, I will start going into technological details. And in general, RGB is a client-validated layer on top of Bitcoin. I will be just in a moment explaining what this client validation means. And this gives a set of advantages to RGB over existing smart contracts, digital assets, digital right management systems. The first of all, comparing to all of existing blockchain solutions, RGB is much more scalable in two terms. In terms of speed, because use of the Lightning Network, so it's not more efficient than Lightning Network itself, but it is one of the very few systems that can operate on top of the Lightning Network, and this is the only system that can operate on top of Lightning Network without Lightning Network modification. And it is also scalable in terms of storage requirements, because data are kept only by owners. There is no blockchain that keeps all the data for all nodes in the world. And this means that storing the data in RGB is much cheaper and much more scalable than storing the data in Bitcoin blockchain or any other blockchain. It is quite private. It has no global state, as already described, so the data leaks are much less common than with any other blockchain system when you can have a chain analysis tools. It is more confidential because nothing restricts you from using cutting-edge cryptography and zero-knowledge proofs. Again, unlike with the global consensus systems, blockchains, where introduction of zero knowledge creates global risks of bugs and things. Here, with a client-validated state, only the owner and the issuer, they take specific risks, and there is no global system risk of using the zero knowledge proofs. And the abstraction, as I already described, RGB is ready for future Bitcoin upgrades. Transactions do not keep any data, and if Bitcoin transaction structure will change, it wouldn't create big problems for RGB at all. So the RGB as a system consists of two set of components. The first set of components is related to Bitcoin transaction graph. And in my past presentation, I already been emphasizing that the underlying layer of RGB is not Bitcoin blockchain or Lightning Network. It is more abstract concept of Bitcoin transaction graph, which can be contained within mined blocks or which can be contained within Lightning Network channel. That makes RGB agnostic to the system that actually, to the system it is built on. Either it could be on-chain Bitcoin or off-chain Lightning Network. So here and after, I will be using term not Bitcoin network or Lightning Network, but when I mean both of them, I will be saying Bitcoin transaction graph. So the first set of components related to RGB is based with Bitcoin transaction graph. And basically, we are not here limited only to Bitcoin blockchain or Lightning Network. We can say that it is working in the same way on Liquid or other UTXO-based sidechains, or it will be working on the future multi-party Lightning channels or other types of channels that might be invented, unless there is a Bitcoin transaction that can be validated with the Bitcoin core consensus rules. The RGB will work on top of this system. And the second part to Bitcoin transaction graph is this client validated part. the part of client-validated data. These are the data with a certain predefined structure and certain predefined validation rules, which are linked to the Bitcoin transactions of the first part. And let me show it in a few graphical slides. So on top, we have a Bitcoin transaction graph, either in Bitcoin blocks or Lightning Network channel. And each transaction, of course, consists of inputs on the left side and outputs. And inputs, they reference some other existing outputs, spending them, namely. And with the client-validated side, which is shown on the bottom of the slide, sorry, in blocks on the LAN channel, it's a mistake. I have to remove this part. In the client-validated data, you define some state, which is basically some data of predefined form according to RGB rules, and you assign that state to unique transaction output. So you said that, like again, how you can define uniqueness of Bitcoin transaction. You probably need to name the transaction ID and specify the index of the transaction output within that transaction. That is the unique identification of transaction output used throughout everywhere, basically Bitcoin Core and Lightning Network, in most of the places. So you can define the transaction output with this in this way, and you can assign the state data to this transaction output. And you have to know that this thing, both the state data and this definition of transaction output, they are kept by the client. They are not becoming part of the transaction. They are not becoming part of the Bitcoin blockchain. They are not becoming part of the Lightning Network channel. They are not create any data abuse. And of course, from the Bitcoin transaction, it's impossible to guess that there are some data kept by somebody are referencing this transaction output, because you basically can't do that without having those client-validated data. And meaning that it allows that scalability, and it allows to build such things on top of Lightning Network without modification of the Lightning Network itself. Yeah, I think we can move forward. And when this transaction output is spent, the transaction output you assign some state data to. In terms of RGB, it means a special event. It means that these rights that you have been assigned to these transaction output are now invalidated. They have changed. And because it is only you, the owner, who can spend the transaction output, only you control Bitcoin script in that output, you have a chance to define some new data. And in the transaction that spends this output, you have to commit to some new state, to the data of the new state. And this commitment has to become a part of the transaction. However, due to homomorphic properties of public keys on elliptic curves, this commitment doesn't increase the storage requirements. So basically, you tweak the public key, meaning that you add some homomorphic data to that, and it works like very confidential way, and it works without increasing the size of the transaction itself. So here on this slide, I'm showing the primitive of RGB, and RGB is built on these primitives. Unfortunately, it's much more complex than the system shown on this slide, and I will be trying to explain that complexity, why it happens, and how this basic structure is changed with RGB system. But again, here we see the demonstration of a very simple principle called single-use seals. And the single-use seals is the thing in the middle that unites the world of Bitcoin transactions and the world of client-validated data. The concept of the single-use seals were introduced by Peter Todd. For RGB purposes, we had to modify it, and again, I will be explaining that further. So we will have quite a detailed overview of all these parts on Bitcoin transaction graph, with deterministic Bitcoin commitments, on single-use seals, how they are constructed, how they apply to Bitcoin transaction graph, and on client-validated data. Today, I'm just giving the overview before all of those details. And single-use seals, they are links, client-validated data to Bitcoin transactions. They are more than just the timestamps, because many people know about the timestamps, so you just commit to some data in Bitcoin transaction like I've shown here with the blue arrow, but it wouldn't work if you just do a commitment. You need to have a unique history of the commitments. The history with steps that can be linked to each other and with which you can prove that there were no alternative history being created. Otherwise, you will be able, for instance, to double spend an assets with RGB. That's why single-use seals is more a complex thing than just a timestamps. And single-use seals, we had to extend it from the original P2P concept to enable many-to-many linking, meaning that each Bitcoin transaction output may have a lot of different client-validated data assigned. And this actually introduced some complexity to the RGB comparing to what I just have shown on this slide. And the client-validated data on top of the single-use seals, which I already described previously. So the single-use seal, as a definition, is an agreement on some future commitment. So you are literally committing to do a particular type of commitment in the future. So it's a second derivative of the timestamping or of the commitment idea. So you agree on where the commitment will happen in the future and which form this commitment will take. In other words, single-use seal is the promise by some party, let's name it Alice, to Bob, to other party, Bob, to create a commitment to some message at a very well-defined point, defined in time space or any other form of phase space. And Bitcoin blockchain is one of these phase spaces that can be used for as a single-use seal medium. And this point is named seal, and the process of its definition is named seal definition. And when Alice creates a commitment to that message, in fact, at that well-defined point, she closes the seal over a particular message. So here, with a red arrow, we define a single-use seal using Bitcoin transaction graph as underlying medium. And when we spend that transaction output, which is defined as a seal, we close the seal over a message, which is some new data. And we close it by committing to this data from the transaction spending this output, which is shown with a blue arrow. So before I'm going to the last part, I will probably again give some time for questions.
Could you elaborate on, so a few slides ago you mentioned that this could be combined with Liquid. Can you elaborate on what exactly that means? I mean, so Liquid has a completely different asset issuance mechanism, right? And my understanding of RGB is that it's similar to colored coins, so there's going to be two different assets. What would it mean to transfer a Liquid asset on RGB or issue an asset on RGB with a parent chain being Liquid?
I'm not sure entirely what you mean by RGB being equivalent to colored coins, because I frequently hear this statement, but the more I'm doing RGB, the less I understand what is common between them.
Well, I guess just could you elaborate what and how you do anything with Liquid and RGB? That would be different than Bitcoin.
Yeah, I will try to do that and just answer more questions if I'm not sticking to your original question. With Liquid, you just still have the same Bitcoin transaction graph. The transactions, they have additional data, which can be used for confidential assets and so on and so forth. But the idea that there is a difference between liquid and confidential assets. We need to understand that confidential assets is one of the liquid applications, or applications on top of liquid. So RGB can be combined and used on top of liquid, but not on top of confidential assets. I think that's quite clear. So we use the same transaction graph from liquid to assign some assets, and basically RGB works on liquid the same way it works on top of Bitcoin or on top of Lightning Network. And the RGB itself, in terms of confidential assets, the RGB can be seen as further development of confidential assets idea. Basically, RGB in certain sense is confidential assets removed from the transaction structure with some enhanced properties. So if I will be comparing RGB to some existing systems, I will compare them, first of all, to the next stage of confidential assets evolution, rather than to previous concepts like colored coins or Bolt or Omni, layer.
Cool, thank you.
Does it answer the questions? Because I'm not sure that I got it exactly.
Yes.
Okay. Any other questions? Okay, so for doing such system as RGB, for doing all this digital right management with RGB that we've been discussing, what we will need to. First of all, we will need ability to assign state to specific unspent transaction output. And we do that with a single use seal definition. So the RGB is consisting of a set of technologies. And to disassemble RGB into simple part, I define these technologies, and here we define the structure, and the first of those technologies is single-use seals. Single-use seals actually defines the unspent transaction output, which will control the ownership of particular rights. The next thing that we should do is to commit to the new state once this output is spent, using another technology, which is called deterministic Bitcoin commitments. And the last thing we have to do is to have standards for defining, serializing, and committing to a state data, and define rules of this state evolution. So this is the actual third part of RGB, next to single-use seals and deterministic Bitcoin commitments. And on this slide, I'm trying to put in some certain way how RGB structure is looking like. So the RGB is basically a directed acyclic graph of state transitions, of these state changes within RGB system, which are validated by on the client side using some schema and simplicity scripts, which I will be describing later. And these data are bound to Bitcoin blockchain using single-use seals that does a state assignment and deterministic Bitcoin commitments, preventing double commitments to specific transaction outputs, meaning that if you assign some state, you can't have a double action on that state. If you spend that transaction output, you can only spend it once, and you have only one way of committing to the next following state. And of course, this operates on top of Bitcoin transaction graph in blockchain, in either blockchain or in a state channel like Lightning Network. And this Bitcoin transaction graph defines the state ownership rules. Additional to these three blocks, there is a fourth block that we actually need. Because you can easily imagine the situation where you use the same Bitcoin transaction output twice, and you assign two different state data to the same Bitcoin transaction output. Meaning that if you spend this Bitcoin transaction output, you have to create new commitments to both of those original states, and you have to combine two different commitments, and desirably you need to separate them in a confidential way, because you can transfer those assets or state rights to other parties, and you don't want one party from seeing the other party information. So you need to combine them in a very confidential way into a single Bitcoin transaction commitment in the transaction that spans that output. And this is actually the point which defines why we need to extend quite a simple concept of single-use seals by P2P for Bitcoin RGB application, because again here you have two seals defined for the same output, and instead of a linear structure of single-use seals, you get quite a complex graph of different smart contracts using the same transaction outputs. And that's why we need this fourth point, additional to single-use seals, deterministic Bitcoin commitments, serialization and commitment, state structure. We need to merge multiple assignments and related state change data into a single operation with multi-message commitments and so-called anchors. So these are the four building blocks of RGB, which I will be presenting in more details over the next presentations. Questions? I heard somebody was trying to raise a question. Okay, probably not.
Hey, can you hear me?
Yeah, go on.
You described the state as a directed acyclic graph. This seems unusual to me because Bitcoin is a tree, right? So that means that there's a merge operation. What is the merge operation? In other words, what is the state transition in RGB which has two parents, two or more parents?
Well, Bitcoin transaction graph is the directed acyclic graph itself. It can be organized as a sequence, linear sequence of blocks in Bitcoin blockchain. But if we, at the level of RGB, we are talking about Bitcoin transactions, not Bitcoin blocks. So we still use the graph, not just a linear sequence. And RGB also, the problem with RGB, that it is a manifold of graphs on top of Bitcoin transaction graph. So each time when you issue an RGB contract, like you issue an asset or you create potentially an identity or something else with RGB, you create RGB genesis, after which you will have a graph, another directed acyclic graph of RGB data, of the state transitions of RGB data. And this graph is linked using single-use seals to Bitcoin transaction graph. So you have a graph on top of graph. And one of these graphs resides within Bitcoin world, like Bitcoin blockchain or Lightning Network channel, and the other graph resides within client-validated domain. The next problem that you will have multiple RGB graphs. Like somebody will issue one asset, you will issue another asset, and somebody will issue another asset, and somebody digital identity, and somebody something else. And eventually, you may own the Bitcoin transaction output, which will be assigned multiple coin states and everything from RGB, and all of them will have independent genesis. So basically, you will end up with a multiplicity, which I call the manifold, of RGB directed acyclic graphs on top of RGB, or on top of Bitcoin transaction graph. So it's very multidimensional thing, and that's what I was saying, that because of this multidimensionality nature, we need additional layer between the Bitcoin blockchain, between Bitcoin transaction graph. Here I'm showing without that layer, and here I introduce that layer, which allows you to reduce the complexity of many-to-many relations between Bitcoin transaction graph outputs and RGB graphs and different state transition in RGB graph. And this is called multi-message commitments, or you can think about this as a sharding technology. Which is not, because sharding is a very strict technological term. However, because of Ethereum, they started using it for whatever purpose. And basically, it's a way of doing the sharding in non-Ethereum way, in a much more proper way. Basically, when each smart contract is a separate shard, because each RGB genesis creates an independent graph which know how it intersects with other RGB graphs, even if they utilize and use the same Bitcoin transaction outputs. And this is done with these multi-message commitments and anchors. And this is actually one of main reasons why RGB is quite complex, and I will be spending quite a lot of time over the next sessions explaining the difference between RGB state transitions, which are always related to a certain RGB contract, and anchors, which may cover many RGB state transitions from many different RGB contracts, and which links them to Bitcoin transaction, and how it's all organized in a way that, first of all, you will be able to validate this data and make sure that there is no double spending, no double commitments, and on the other part, that this structure is very confidential, meaning that the shards or this independent history of RGB state are completely independent, and if you need to send somebody, for instance, USD Tether over RGB, and you need to make sure that this party wouldn't see you, I don't know, Amazon shares that you had on the same transaction output, you can do it in a very confidential way, so nobody will even be able to guess that you had Amazon shares on the same transaction output. And this is done with these anchors. So that's basically a very high-level overview. So did it happen to your question, to answer your question?
Yes, sorry, my mistake about the direct acyclic graph. You're completely right.
Okay, so concluding this presentation, in RGB, we have a set of layers. And these layers are very well separated within the code base that we have today. Because of this complexity that I just described, we really need a very modular and layerized structure to make the audit and make sure that RGB is functioning properly. And these layers separated across two main software components. The first software component is called LNPBP core library. It's Rust LNPBP repository in GitHub, and it contains the primitives out of which RGB is built. And these primitives are consisting in four main modules. The first one are generic paradigms for building layers on top of Bitcoin and Lightning Network. And these generic paradigms, here you see in the first column, them are these paradigms that I just described on this slide here. And they include, first of all, an encoding rules to make a commitments and encoding of state data very deterministic and well-defined. Of course, they use cryptographic commitments for making sure that the history of RGB is immutable, at least giving the underlying Bitcoin transaction graph immutability. The single-use seals I've been talking about, and the client-side validation specific things. On top of that, there are modules related to Bitcoin network, the extension of the basic Bitcoin functionality. First of all, primarily related to cryptographic commitments, and application of cryptographic commitments to Bitcoin transactions are named deterministic Bitcoin commitments, and single-use seals, which application to Bitcoin graph is named transaction output-based seals, XOR seals. And these seals are using these Bitcoin commitments, deterministic Bitcoin commitments, to make sure that the next state, the next change is strictly committed to. So as I said, in LNPBP core library, there are layers of these generic paradigms of this cyan color. And on top of that, we have extensions to Bitcoin protocol with this orange color, extensions to Lightning protocol, not showing on the slides so far, just not to introduce more complexity, and RGB core data structure shown here with a red color in the last column. And with the RGB structures in the module of RGB, we are building a consensus encoding specific to RGB using the strict encoding primitives. We built a consensus commitments using that encoding, joining it with the cryptographic commitments primitives. We built RGB state transitions, encores, assignments, consignments, and schema data using single-use seals and schema. I know that it's a lot of terms, and I will be gradually explaining them, coming up to the large-scale structures, RGB structures, such as contracts and stash. And the stash is the data structure that actually has all the data to all the state and different RGB graphs that are owned by a specific party, like the thing that will be maintained by your wallet. And the RGB schema is a set of standards that defines the validation rules for RGB state. So that's the second part. You remember that with the first part, we had ownership at the top of this slide. It is managed by Bitcoin script. It can be bare Bitcoin script, hashed or taproot, supporting multi-sig, state channels, atomic swaps, whatever. You can use even scriptless scripts with adapter signatures and whatever is required. This is ownership layer. It's maintained by Bitcoin blockchain and Bitcoin transactions, basically. And RGB layer, the client-side state validation, and it includes schema and simplicity scripting language. So another recap, with RGB contracts, we have main three core RGB smart contract components, namely the state, the data, which are assigned to specific Bitcoin transaction outputs using single-use seals, the schema that defines which state can be out there, can exist under a certain RGB contract and how it can evolve in time, and scripts, which define state validation rules using simplicity language. I will run quickly because it's really, I already used all of my time. So comparing to Ethereum style smart contracts, I started with this idea that RGB is quite different. And it is quite different in many aspects. First of all, the parties of the agreement, because smart contract is always an agreement. Contract is agreement, even if it is smart. And the parties of the agreement, in case of Ethereum style, they're very loosely defined. It's like a world contract, a world computing. It's really hard to guess who affects the contract, because like we had with the DAO hack, it was the situation where miners, who was not a part of the agreement and not owners of the tokens, they actually took a decision on the smart contract state and its evolution. Unlike that, with RGB, the only parties of the agreements are the issuer and the current owners, and no miners can't know how affect them. The agreement, in case of usual smart contracts, is stored in blockchain, and it requires some additional application binary interface information, while with RGB, it is stored by the clients, by the actual owners, and within the state transition and genesis. The current state in Ethereum style is contracts, in Ethereum style smart contracts, is blockchain stored. It is publicly visible, non-confidential, not scalable, without second layer support, which is very different to RGB, where you have the client stored data. They make impossible to have any chain analysis. They're confidential, scalable, and support second layer. And the state change rules and ownership rights in Ethereum style contracts, both governed by EVM code, while in RGB they're separated. And the ownership rights are managed by Bitcoin script and Bitcoin layer, while the state change rules are managed by schema and simplicity scripts. And very interesting with immutability, like I already mentioned, DAO hack, Ethereum claims immutability, but it's pseudo-immutable because it is immutable in promise, but censored by miners and network creators by fact. While with RGB, there are very, very well-defined mutability rights at genesis and schema level by issuer. So you can create a contract that can evolve, that can even update its own scripts, but these updates may happen only by well-defined parties, because again, they are managed by the same digital right management rules like RGB defines itself. And it is mutable only by new owners. The issuer can't change them arbitrarily without agreeing with the owners that are already out there. So, yeah, probably this was the last slide. I think it's better to recap and have a question and answer section. I understand that it was quite complex, no matter how I tried to make it less complex.
I think your presentation might have been overwhelming. And we spent already an hour for it. But guys, if you have any questions, feel free to ask them.
I would like to know more about how the single-use seals work. Are you going to address that in a future talk, or do you want to address it now?
Yeah, unfortunately for single-use seals, we will have to have a specific dedicated talk because of the more complex nature.
Cool, I look forward to that.
I think it will be then the next presentation that we will have. And also it will be just not a single-use seal explanation. My goal is to get into the links to specific code parts related to the single-use seals in existing libraries. Any other questions?
Yeah, I had a quick question about the anchoring assets to like specific UTXOs or addresses. So is that going to be addressed in another talk? So, for example, if you have specific RGB assets that are anchored to, say, a Lightning channel, for example, and then an uncooperative close occurs, I'm assuming what happens to those assets will be decided at the client side, like the RGB node, for example.
Well, whatever happens to assets in case of non-cooperative closure will be the same what will happen to the Bitcoins inside the same channel. So it will be actually managed not by RGB node, but by existing Lightning node used by the client.
Got it. Okay.
So that's the beauty of RGB is very complex by one hand, but very simple on the other. The beauty of its simplicity is basically we get rid of so many problems because all of those problems are managed by existing Bitcoin and Lightning network. And we just use all of that. So we already have an asset in Bitcoin network and Lightning network, which is Bitcoin, Satoshis. And it has very advanced way of keeping it and managing all the non-cooperative channel closures and other issues. And RGB is using all this infrastructure, adding nothing on top. Literally, all the tasks, all the job will be done by Bitcoin Core, by Lightning node, and not RGB node itself.
Gotcha, that makes sense. I'm just curious, maybe a little bit more about how like what's the relation to like the assets that are issued in RGB, you know, compared to the actual underlying, you know, UTXOs or channels that it's anchored to. So for example, if I have a Lightning channel that has, you know, maybe, you know, $20 worth of Bitcoin in it, and I have, you know, $1,000 in that Lightning channel, you know, of RGB assets that are anchored to that Lightning channel, and an uncooperative close happens. I'm assuming there's some relation of like the actual like amount of Satoshis to RGB assets. Is that right?
Can you repeat the question, actual? Because
Yeah, I'm guessing that there's some relation of the amount of Satoshis in the channel to a certain amount of RGB assets. So, for example, if I have, you know, $20 in a Lightning channel of Satoshis of Bitcoin in the Lightning channel, and then anchored to that is, you know, $1,000 of say RGB USDT, and an uncooperative close occurs with that Lightning channel, I'm assuming there's, you know, some relation of the amount of Bitcoin in that channel to RGB assets, or something like that. Is that correct?
No, there is no predefined relation. You will just need Bitcoins to be able to maintain on-chain transaction fees when the channel will be closed. And of course, you in the most of cases, you will have much more valuable RGB assets in the channel than you have a very small amount of Satoshis required by the consensus rules. But still, the software behaves in a way that, for instance, none of existing Lightning node, they give any care of the actual values of the Satoshis that are within the channel. They manage the non-cooperative closing in the same way, no matter do you have 20 Satoshis there or 2 billions.
Got it. Okay, so that'll all be determined client side essentially.
Yes.
Cool. Thanks.
Can you hear me?
Yeah.
So what my understanding is that if you have tokens in a RGB channel, Lightning channel, then you wouldn't be using that channel to forward or to run regular Bitcoin payments, do you?
No, you wouldn't. With the design that we have, you have a single asset channel. So this channel will have a single operational asset it will operate in.
Exactly. So the Bitcoin stuck in there in that channel would be just for paying for on-chain fees and
correct
for the security of the channel itself, but its purpose is just RGB only.
I wouldn't say even for security of channel, just for on-chain transaction fees.
Yeah, which is somehow security related in the sense that you cannot so there's always a punishment, and the punishment is described in Satoshis and in Bitcoin. I have another more maybe farther away question.
I will correct that, because in case of RGB, the punishment will be defined in RGB tokens as well. Well, there will be a punishment in Satoshis, but the security will be related to RGB value.
Sure, right. Sorry for the mistake.
No problem.
How can all this relate to discrete log contracts? So I remember you were talking about discrete log contracts at some point in the past. Would they be somehow replacing the job that simplicity is doing, or something parallel or on top of it, or?
They are completely distinct domains. So with DLCs, it will be a separate component towards Bitcoin script or simplicity language. So DLC is a way, it's basically a scriptless scripts or something like that, a way to control the external events with oracles, with potentially decentralized oracles. And it is a way that will enhance the digital rights management. So with Bitcoin script, you define the owner. And with the Bitcoin script, enhanced by DLC mechanism, which is basically embedded into Bitcoin transaction with adapter signatures, you define the special conditions of enforcing some particular ownership change. Like, for instance, if you would not reach agreement with the other party, there could be a third party, which signature can be used to force contract execution. And at this level, it knows how it interacts with RGB. So RGB, again, just utilizes that property of Bitcoin transaction. So Bitcoin transaction is enhanced with a DLC mechanism, while RGB is just inheriting all this goodness from Bitcoin transaction layer.
Okay.
In other words, that's why I spent so much time trying to explain the separation of two concepts, which is very unusual for a smart contract world. The concept of rights ownership or ownership, and the concept of RGB state evolution.
Clear. That was my question. I wasn't able to pose it correctly, but my question was, would DLC affect state ownership or state validation part?
Only state ownership.
Okay. Thank you.
So, yeah, again, I will try to explain it in different words. If you have RGB assets, for instance, again, USD tether, you have 1,000 of USD tethers on some Bitcoin transaction output. The rights management makes sure, rights management related to Bitcoin script and potential to DLC, make sure that nobody else than you and a party is well defined within that Bitcoin script is able to spend those 1,000 USD tether. They ensure the security of your funds and the spending rules. So, for instance, it might be that it's just a single signature that is required, and meaning that only you are able to spend those 1,000 of USD tether. Or it might be 3 or 5 multi-sig, meaning that any 3 or 5 participants can spend 1,000 tether. And it is ensured at the Bitcoin transaction level. In the same way, it might be a DLC contract or HTLC contract within the Lightning channel. But again, it is Bitcoin script that ensures that the ownership rights of the assets are forced. And they are forced at Bitcoin transaction layer level with Bitcoin script. What RGB validation rules makes on top of that? They make sure that each time you spend 1,000 USD tether, you can spend not more than 1,000. So you had 1,000 and you pay to 2 other parties, but the sum of tokens you paid must be equal to the sum of your inputs, meaning 1,000 in this case. And you can't do that with a Bitcoin script. And it's here, this is a situation where RGB schema, and for more complex cases, simplicity scripts, comes at hand. It validates the state evolution, not the right to spend, but how the state changes when you already have spent this Bitcoin transaction output. Does it make sense?
Yeah, it's absolutely a lot clearer than before. I don't want to monopolize the conversation, but would in this case be possible to use DLC to, for example, define how one can trade 2 different RGB tokens between each other, given an oracle that gives the relative price between them?
Well, you will do it in the same way you do it with Bitcoins. And for instance, if you have Bitcoin and Lightning and what's the name, Litecoin, for instance, to cross-chain.
It's an atomic swap, basically.
Yeah, it's an atomic swap. So again, it's nothing about RGB in this case. It's just you trade not within two different blockchains. You trade within Bitcoin blockchain with a different amount in Satoshis, but different amount in RGB on top of that. So RGB layers knows about the value, but all the validation and security is, of course, enforced at Bitcoin level, not at RGB level.
Thank you very much.
Yeah.
Can you hear me?
Yeah.
Okay. Sorry. I had a question when earlier on we're like making these state commitments to either Bitcoin or Lightning or some other base layer. And I'm wondering if the clients set the frequency of these commitments based on like the definition of their like a shared state machine, or what exactly decides how often they need to commit to a different state update?
Yeah, the rule is straightforward. Each time you need to update the state, you need to spend transaction output. Each time you spend transaction output, you need to commit to a new state. So the frequency of the state commitments is the frequency how often you would like to update your state. If you'd like to do that oftenly, of course, it's reasonable not to do that on-chain, but to create a Lightning channel and do these updates within the channel without publishing new transactions into Bitcoin blockchain. Have I answered the question?
Yeah, sorry. The audio cut out at the end. You said it's reasonable to like not do that on chain, but to do it, I assume you mean like Lightning or some other payment channel there?
Yeah. So the frequency of commitments is the frequency of your state updates. So you need to commit only when you pay somebody. Only when you transfer to somebody some of existing assets. And at that case, you spend the transaction output, create new transaction, and you commit to the new state. So if you have to do that frequently, it's desirable to do that within Lightning channel.
Okay, that makes sense. And I guess when we're operating on like a Lightning channel, are we then embedding the state data, I guess, in terms of like HTLC updates or so instead of like TX outputs? Or
we just update commitment transaction. HTLCs are used as a way of forcing multi-hop payments. So you create new commitment transaction, which commits to the new state. It is the same way that when you change the balance between you and the other party, you use the updated version of the commitment transaction. It is the fact that this update of the commitment transaction technically happens first through creation of new HTLC output and HTLC transaction, basically two transactions, HTLC transaction, and then it again being reduced to the updated version of commitment transaction, which without those HTLC outputs. So HTLC is just a way of ensuring that the updates are happening in a safe manner for multi-hop payments.
okay, that makes sense. Thank you.
Yeah, you're welcome. Any other questions?
Hi, am I audible? Hello.
Okay. Hello.
Yeah, am I audible?
Yes, sure.
Yeah, you're audible. Yeah.
Okay, so I was just trying to make a map of what it might look like with Lightning. So I just had the question is like, so when you were saying like there is we can do this state transition through a Lightning channel, does it mean like if suppose Alice and Bob wants to transfer some RGB tokens or some USDT based on RGB, like Alice has some amount and he wants to give it to Bob, so he wants to make the state transition, and when she is doing it through the Lightning channel, channel. So is the channel is between Alice and Bob, or the channel is between Alice and Carol and Bob, and all Alice just needs is just a route through the Lightning Network to Bob, or just or she also needs to have a direct channel between Bob so that she can update the commitment transaction. So what is exactly the channel configuration in the Lightning side?
It works both ways. The only requirement when you have non-direct channel, you need to have sufficient liquidity over the specific route. If you don't have a direct channel and don't have a sufficient liquidity, you may use another mechanism of decentralized exchange, which will be developed in future. So to summarize, there are three ways of doing this. First of all, you can have a direct channel with a sufficient outbound liquidity, and it's simple. You can have a multi-hop channel with a sufficient liquidity over the whole route, and you can also do that in the same way like with a direct channel, because the technological mechanism of Lightning Network updates are the same in both cases, with HTLC and the rest. Or if you don't have a direct channel and don't have a route with efficient liquidity, you may use an exchange over the route mechanism if you have the parties willing to do that exchange and still do the transfer. But it will involve more than just a simple RGB and additional modules, which are also planned to be developed.
Okay, right, that makes sense. So so I guess for like start, it's like easy to think about, like whenever we are talking about transferring assets through Lightning, it means like we have a channel and we are just updating the commitment transaction between that channel. So is that a correct way to think about it?
On the first estimation, it is correct. It is also required to remember that, in fact, each time you update a commitment transaction, you do it through HTLC mechanism, even if you have a direct channel, technically. So it's multi-stage process. First, you update commitment transaction, you add two transaction outputs, and you add HTLC transactions to that, and then you update commitment transaction second time, removing these two HTLC outputs.
Okay, right, makes sense. Thanks.
You're welcome. Any other questions?
I think we can wrap this up. It's been an hour and a half. So guys, this recording will be uploaded as a YouTube video. So I will post the link to the Q&A chat. And feel free to ask questions in GitHub or in Telegram chat. Thanks for being here.
Just one question, I probably missed it. Like, is there plan of having this presentation and later to be continued, maybe next week or something?
It is planned.
Okay,
well,
cool.
We will certainly continue this presentation. The only question, would it happen over the Wednesdays, or we will have a dedicated day for such technical calls? But we will sure let know all of our contributors and developers involved in the.
Okay, cool.
Awesome. Thank you, guys. See you.
Hey, thanks for hosting.
Thank you. Thanks.
Thank you.
Bye.
Bye.
Thank you.